today, we're in chapter 14 now, right? And so this is 14.4, and the section is called partial derivatives. So this is different. And why is it different? I want to go to your book. I tell you, I'm thrilled because I can teach with this ebook. In some ways, I think that this is such an advantage that we have over even just the last time I taught the course. There's some really nice visuals that explain what's going on. And so if you look at what I'm going to cover, I'm going to talk about, first of all, derivatives with two variables, because the functions we're talking about, right, look like this. Instead of y equals f of x, not just this, but we're going to have z is a function of x and y, right? And so now, I mean, the question is, you know, it used to be y prime was f prime of x, right? That's what I used to do. And yes, this told me the rate of change or the slope of the tangent line. Now the question is, how do I generalize that idea here? And when you guys say, well, it tells you the rate of change, or it tells you the slope of the tangent line, that's weird already in 3 dimensions. And so the picture that shows that really nicely in your book, they go here. They say, okay, guys, here is a typical function, right? So a function tells you how high we are for a given x and y, given input and output. And so it's a surface. And they say, okay, suppose you're at this point here, 0, 0, and however high it is, right? So they show a man right here, okay, who could travel east or travel north, right? So I guess the question is, what's the slope of the tangent line for this guy? Is it positive or is it negative? Yeah, what's his rate of change? Like you said, depends. If he's walking north, he's walking downhill. But if he's walking east, he's walking uphill. You see that? So it's more complicated, just adding one dimension to the problem. And so we deal with that by taking what are called partial derivatives. Okay? Derivatives with respect to x and derivatives with respect to y. And so what we will do we will compute two different derivatives. And really, I should put the word partial derivatives. Okay? So maybe the idea is to hold one variable fixed, or treat it as a constant. Okay? So I'm going to show you the picture, and then maybe we'll do some examples. Because again, the picture shows you what you're really doing. Here's the definition of what you might call the partial derivative with respect to x. Now, if you look at the picture here, well, look above. It says the limit as h goes to 0, that's our difference quotient, right? But if you notice, we still have x plus h, but you see how it says comma b? It doesn't say comma y, because we're gonna say that y equals b no matter what. And so on the picture here, here's my function, this surface, but you see this rectangle? That's the plane y equals b. And so I'm saying, okay, here's the point where I'm at, this little point where they're drawing a blue tangent line. I'm saying that I'm going to be at that point, right? And so I'm saying that this y equals b is constant. I guess I can change the point, right? I can move a somewhere else. But what I'm looking at is this point of tangency right here. The blue line is the point of tangency. Okay? I actually don't like showing the line y equals. Oh, okay, yeah, if we get rid of that, that's the plane we'll get rid of. That's okay. But do you guys see what's happening there? Here I'm changing b. I can move the plane somewhere else. And then the other thing they let me do is change h. Oh yeah, this is your Calc 1 problem all over again, right? What is the slope of the tangent line? How do you get it? It's the limit as h goes to 0, right? So right now h is 1.7. What kind of lines are these green ones that I'm drawing? Do you remember what these are called? Secant lines. Okay, you guys learned your Calc 1 really well. And as the secant lines approach, eventually they become, well, yeah, if you can get it to be 0, it would be tangent, right? But we can't. We just take the limit. Okay? So that's your Calc 1 over again, is happening in a certain plane. This is called the partial derivative with respect to x. We also have the partial derivative with respect to y. Oh, by the way, the easiest notation is this one, fx. Okay? So maybe I should say that on our notes. Okay, so we have fx would be this one. Or, and for this one, maybe I'll go into a little more detail on the notes, since we already saw the picture of fx. How about fy of xy? Okay, so again, this is the partial derivative with respect to y. Okay? And so, how do you define this? This equals the limit as h approaches 0 of what? Well, I used to tell my Calc 1 students when they were doing a problem like this. Jimmy asked me, are we going to doing these long way problems? I used to tell people, first of all, I'll do the denominator for you. Right? That was easy. Then I used to tell people, put what's after the subtraction sign first. So we used to write minus f of x. But in this case, we're going to write minus f of what? Well, it would be x comma y, but let's think about what we're going to do. When we say we're going to hold one variable fixed and treat it as a constant, which variable will I be holding fixed this time? We're going to hold x fixed. In the first problem, we held y fixed, and when we took the derivative with respect to x. So actually, we're going to hold x fixed to some value. I bet the book is going to say a. And then y, this is going to be a function of y only, in a sense, right? We're going to hold x fixed. Let me see if I can, if I'm right on that. Am I writing it correctly? Let's go down to that.
Well, why for that one did they get minus f of x comma b? Why did they make it a b?
Oh, yeah.
It doesn't look like they held anything.
The reason they're doing that, that's a good point. So yeah, I guess we would, Right. The reason they're doing this is because they're trying to say what happens at the point A comma B. So kind of like, back in Calc 1, we had this, right? Where to go? We would do f prime of x, and then later we might do f prime of some number. So that's what they're doing, is they're trying, because this would actually be the slope of a tangent line, whereas this is a formula for a slope of a tangent line if you put a number in. Okay? So they're trying to make it so that you can actually see it. And so I can change b. Let me change b, actually, because I kind of don't like where it is. That's better. There's b. Right? But again, x equals a is what we fixed. We fixed some plane that we're working in. And then again, I don't like h being where it is. Well, okay, doesn't matter. Blue is the tangent line. Green is the secant line. Okay? So, okay, back to here. Oh yeah, so what goes up here? Well, I guess it would be f of what? A is fixed. We're in the plane x equals a, and so it would be y plus h minus f of a y all over h. And so if you think about it, all your old derivative rules are going to work still. Because if you hold the x input constant, you've just, on the picture, restricted yourself to this plane, x equals a. And so we're in the Calc 1 world, right? One nice thing about doing derivatives this way is that you are in the Calc 1 world, which means all your old rules still work. So I guess what I should do very soon for you guys is examples, or else we're going to be in trouble. Right? So let me give you an example. And then we'll also look at some in the book as needed. Okay? I'm going to give you one that I think I gave you guys earlier. Was this the one on your test, or was it in the notes? I think this was not the one on the last problem of the test, was it?
No.
No, but this was in the notes. Yeah, we saw this. What do you guys know about this function? Well, first of all, this function's not defined everywhere, is it? It's not defined if what happens? I guess it's almost defined everywhere. So, yeah, except the origin. So we'll define it this way unless x equals y equals 0. So it's not defined at the origin. So then we'll say at the origin, what do you want to make it equal? Okay, I'll make it equal 0. All right, so we have a function. Actually, in the notes, do you remember what was special about this function? It'll come back. That's all right. I'll bring it up shortly. All right? So anyways, what I'd like to do is I'd like to compute f of x. Okay? So A here, let's compute fx. So let's see. How do I compute the partial with respect to x? Well, the answer is, again, treat y as a what? As a constant. That's right, Duncan. So let's do that. So let's see. This is the old quotient rule, right? Which actually, some of you guys didn't do that on the test. I was a little annoyed when you saw something like this. I said take the derivative. Oh, I know what it was. I said take the derivative of the curvature function. And the curvature function was like 2x cubed over something to the 3/2 power, right?
Yeah.
So you need a quotient rule for that. All right, well, let's do it here. So the quotient rule still works, okay? So it's HODI high. So it's x squared plus y squared, that's the denominator, times the derivative of the numerator. Now you have to think about this. When you take the derivative of the numerator, you don't need a product rule, even though you might think you would. And the reason I don't is I'm computing fx, the derivative of f, the partial with respect to x. Okay? And so we're treating y as a constant. And if this said x times 5, you would actually write 5x. What's the derivative of 5x? So what's the derivative of xy? It's y, because you're treating y as a constant. Does that make sense? Minus, hi-de-ho, well, xy is my numerator. And now I need the derivative of the denominator, which is going to be 2x plus 0. Y plus 0. We're treating that as a constant. That's right. All over what? Ho ho. X squared plus y squared squared. Okay? So can I simplify this? I guess so. I mean, you can see you're going to get an x squared y, but then you're going to subtract 2x squared y. So what I would end up doing to simplify this is I would write y cubed from this piece, and then minus an x squared y all over x squared plus y squared squared. So this is my formula for the partial derivative. Notice it's a function of x and y, just like the original function was. And this can tell you slopes of tangent lines, kind of like we saw in the picture. Okay. I guess as an exercise, I could have you guys compute Fy, but I'm not going to. And the reason I'm not going to is I'm going to point out that your formula would look extremely similar to what you just saw. Whoa. Why would it look so similar? Because, oh, and I see what happened. So again, Fy here, I'm telling you that because x and y are basically the same, appear the same number of times in the numerator and denominator, it probably won't surprise you to realize that this is what you would get. X cubed minus y squared x over, and I'll still write it as x squared plus y squared squared. I guess it would come out y squared plus x squared squared, but that's the same thing. Do you guys believe that that's what we would get if we worked it out? Yeah. Okay. Obviously, you're going to need to practice doing partial derivatives. I've done one example. Okay. The book does a lot. Let's take a look at some of theirs, and you tell me if you want to try any in class or if we should just keep moving. Here's some. Oh, that's something I should mention. Look at that funny notation. See what it says for part A for this example 1? Compute. Do you know whose notation that is? Leibniz. That's right, Leibniz notation. But Greek is also correct here because, what do you notice? Leibniz notation back in Calc 1, here, let me go back to it. When we used to write f prime of x, there was another way to write that, right? We could write, instead of y prime, we could write dy dx, right? But when you do a partial derivative, okay, a partial derivative, another way to write this is curly d, or delta, really? But it's really more of a curly d. Curly d f curly dx, okay? The curly d tells you this is a partial derivative as opposed to something else. Okay? So it's basically telling you, hey, we held one of the variables constant when we did the derivative. So this is curly df, curly dy. Okay? That's not the correct way to say it. Actually, your book tells you. Where'd they do that? I thought that was really cool. Oh, I know. Yeah, the table where they talk about higher order. Here, let me jump down just a second. Yeah. See, guys? You look at what I have to cover today, right? So back in Calc 1, after we did first derivatives, we learned about the second derivative. What did the second derivative tell you guys? Acceleration. It also told you concave up, and concave down. Remember that? Inflection points, yep. So there are higher order partial derivatives. And look at that. There's lots of them. Why are there lots of them? Because there can be, right. Like after you compute fx, you can either compute fxx or fxy of those things. Okay, so d squared f, yeah. Ugh. Okay, fine. Anyways, we'll get to that one when needed. But some of the homework is just going to be practice computing derivatives. Example 2, example 1, quick check 1. Any of these we need to do? I'm happy to do one.
When you get there, did you do example, talk for example 5, which was the
Yeah.
about the gas law and volume and pressure?
Oh yeah, that's good. So that's down when you get here, right? Functions of 3 variables. Now, this is kind of the first time I think that we've really talked about this, but if you think about it, there's no reason that you shouldn't be able to do 3 inputs and do Calc 3, except for one thing. We're not going to be able to sketch a graph very easily, are we? Of course, we have tough times graphing in 3 dimensions anyways. But if my function looks like the one you see in example 4, there would be 3 partial derivatives. You see that? By the way, here's a quick question. If I'm going to do second derivatives, how many different second partial derivatives could I get for example 4? Almost. Like just for fx, then you could take x, y, or z for that one. And then for fy, you could take x, y, or z. So wouldn't it be 9? Yeah, 9. Right? Yeah, for the second derivatives, yeah. I mean, this is crazy. Okay, but I think this is what you're talking about, right, Kathy? Ideal gas law. You guys remember this one? My chemistry teacher had this little song we had to sing, PV equals nRT, right? You know that one?
Yeah.
Yeah. And R was 8 point something times 10 to the, I forget. Oh, it depends. So see, I'm out of my league. I don't know my chemistry. But I know that R is a constant, and I know that N's a constant, so in our book we just called it K. Whatever N time. Oh, N's the number of moles? Is that right?
Yeah.
Thank you. All right. I remember something. It was funny when my sister took, or my daughter took chemistry last year. I'm like, yeah, good luck. So PV equals K times T, okay? And so, Kathy, you want me to go over the quick check, or should I go over the whole thing?
No, just that, I don't, not even the quick check, just, I'm comprehending that example.
Comprehending the example itself. Let's do that. All right. So it says we have PV equals KT. Part A, determine the rate of change of the pressure with respect to the volume at constant temperature and interpret the result. This is a really nice exercise. Here we go. So I'm going to start just by writing down the formula. And then it says rate of change, part A, of the pressure with respect to the volume. So where it says rate of change, that makes me think derivative. Right? So you guys thought the same thing I did. And then it says of the pressure with respect to the volume, right? Well, that makes me think about Leibniz notation. I like Leibniz notation sometimes, and sometimes I much prefer Newton notation. But especially when it tells me what I mean by a rate of change, I start thinking what they're asking is the rate of change of pressure with respect to volume. Now, wait a minute. If this were Calc 1, these would have been regular D's. Why did I make them curly? Well, partly because I'm in Calc 3, and partly because it says what? Constant what? Constant temperature. So temperature here is going to be held constant. That's the thing that's the fixed plane, right? And so I guess what I want to do is I want to understand that we want to take this pressure and rewrite it. Pressure is actually equal to K times T divided by V. Does that make sense? Here, pressure is a function of what? Of two different variables. TV. Television. Right? So there's P. And they want me to compute dP dV. Or what's the other notation we can use? We can call it PV. Right? Whichever one you like. So let's do it. Well, let me do it this way. dP dV will equal. All right, how do I do this? Oh, well, wait a minute. I think the easy way to do this is remember that T, we are holding what? Constant. So if we're holding the temperature constant, maybe I should just think of KT as a constant times V to the negative first power. That's probably the easiest way to do it. Because then I don't need the quotient rule or anything like that. I can just say that the partial derivative is going to be negative KT V to the negative second, which is equal to negative KT over V squared. Make sense? And I think the other ones are kind of like that. Explain these results using level curves. What are level curves again? Oh yeah, level curves are where you pick a value for z and then you look at what the function set equal to that value looks like. And so I guess what I'm doing here is I want to talk about pressure, right? Again, we had to solve for pressure. So pressure equals K times T over V, right? So give me a pressure. 10. Nice job, guys. So I can say 10 equals K times T over V. And I can ask you, what the heck does that look like? I don't know. Would it help if instead of using T and V, I used X and Y? Probably would. And so if I did that, then I could multiply both sides by Y, and I could say 10 times Y equals K times X. And what I could now do is I could say that Y is equal to K over 10 X. Hey, what shape is that level curve? Yeah, these level curves are you know, this looks familiar. The level curves actually being lines. I swear I saw that recently. Anyways, but that's what ends up happening. What's that? So the level curves end up being lines, and so the picture that your book gives. Yeah, let's look at that solution, part C. Because then actually, I think the quick check was about the diagram. Yeah, here's the different lines for various pressures. So when I said 10, I guess I was looking at this line. And so, we were holding the temperature constant. So their temperature was their Y value. And they're saying, well, if you're in this world where the temperature is always at this level, and you increase the volume, you're going to be decreasing the pressure. See? As I increase the volume, pressure goes to 40, then down to 30, then down to 20, then eventually down to 10, right? Does that make sense? When I increase volume? Yeah. What happens if I decrease the volume? Then I'm building up the pressure. That's why a balloon will pop if I squeeze it enough. Right? Okay. So, I want to go back to our fun example we had before. F of xy was xy over x squared plus y squared, right? And we computed fx, and we computed fy. Let me write down what those were. You guys could help me. Oh, there it is. Y cubed minus x squared y over x squared plus y squared squared. Was that one? And then this one must have been x cubed minus y squared x over x squared plus y squared squared. Is that right? Yeah? Okay. So you'll notice that the one thing that we didn't talk at all about yet that's in this section is this idea of differentiability. What does that mean again? Differentiability? What did it mean in Calc 1? That's what I'm asking. So it's interesting, yeah, there was this thing about it implies continuity. You have to be continuous if you want to be differentiable. But if you are continuous, does that mean you are differentiable or not necessarily? No. Not necessarily, right? And the classic example was, I may as well draw it here, the absolute value function. Y equals absolute value of x is continuous, but not differentiable where? At the origin. Why? Because you need a little bit more. Differentiability means a little bit more than continuous. It actually means that the limit as h approaches 0 of f of x plus h minus f of x all over h exists. That's what it means. The limit exists. Here, the absolute value function, the limit doesn't exist. Because if I'm on the right-hand side, what's the slope of any tangent line on the right-hand side? I guess it'd be positive 1, right? But what would be the slope of any tangent line on the left-hand side? Negative 1. And so what's the slope of a tangent line here? Well, who knows, right? You can't really define a tangent line there. It could be whatever it wants to be. So that's where we say the limit doesn't exist. We learned back then the right-hand limits and left-hand limits had to both be equal. So here, in the new world, okay, I'm telling you we're going to have some problems talking about differentiability. We're going to need more than just this. So I guess what I'm going to say is it's more complicated than this in Calc 3. So I'll say a little bit about it shortly. But back to our example. You guys, we computed these partial derivatives. Are these partial derivatives defined everywhere? Well, I guess these are defined unless what? Right. If x and y are both 0, then we're out of luck. Okay, that's fine. So what I'm going to do now is I'm going to do an exercise where I say, let's show kind of what we showed here. See, the reason that this function was not differentiable was because if you graphed y prime back in Calc 1, it was either negative 1 or positive 1, right? So y prime is not continuous at the origin. So we're going to kind of show that that happens today also, all right? So I guess my exercise I want to do now is I'm going to show that, how am I going to say it? I'm going to say, show that fx is not continuous well, that's already, we already know that. Okay, let's not just write that down. We already know it's not continuous because it's not even defined at 0, 0. Instead, let me just compute a couple of limits. Let's compute these limits. So here I go. Suppose xy is approaching 0, 0 along the line y equals mx. Oh, that's what I forgot to do with you guys. Okay, this was part B of my plan. Part A, I want to do this. Sorry, guys. We can still define these things. Okay? We can still define fx of 0, 0. So that's what, I guess that's the point I want to make. In Calc 1, you can't even define the derivative here, right? But you're going to see that we can in Calc 3. How do I do it? Well, here I go. So this we'll put on, this part B thing we'll put on hold. Maybe we'll do that after break, because we'll need to recharge. But here I go. Fx of 0, 0 would equal, now you're going to say to me, Paul, you can't do it. You can't plug zeros in here, and I agree. But even though I can't plug it in here, I can go back to my definition of fx. Now what's the definition? It's the limit as h approaches 0 of what? Let's do the denominator. What's the denominator? It's h. We are always subtracting f of something, but if I'm plugging in 0, 0, it's actually 0, 0 right here, right? F of 0, 0. And then here I have f of 0 plus h comma 0. Now you might say to me, hey Paul, f of 0, 0 is not defined. Oh, but wait a minute. On the very beginning, we decided to define it. Remember? We did a piecewise thing, and what did we say? We decided to call it what? Okay, 0 if x equals y equals 0, and this will be usually, right? So if we do that, now we can say that we have the limit as h approaches 0 of what? Well, we're subtracting 0. And what's the numerator? I guess it's f of h comma 0. Right? What would be f of h comma 0? Well, let's plug it in. It's the numerator is 0. And what's the denominator? H squared, right? Divided by h. And what's h squared divided by h? Well, wait a minute. This is 0 over h squared, right? So it's 0 divided by h, so what is it? So it's 0 over h, which is 0. Yeah. So I guess what we did is we defined fx, even though, you know, it doesn't really work in the formula, this shows you that the partial with respect to x is 0. And I'm going to say, similarly, I hope you'll believe me so we don't have to work it out, fy of 0, 0 is 0. Okay? All right, now I'm ready for part B. Suppose that xy approaches 0, 0 along a line, y equals mx. And I'm going to need more paper. Here I go. So again, xy approaching 0, 0 along y equals mx. You might remember this is the example where we always got 0 when this happened. Let's see what happens to the derivatives. So let's see. What I want to compute now is fx of what? Well, since y equals mx, right, I guess what we can do is we can say this is x comma mx, right? Let's compute what that partial derivative looks like. So again, from the formula, let's see, we had y cubed. So y cubed is going to be m cubed x cubed. Is that okay? Minus, what did we have? X squared y, so we have x squared times mx. All over, and this is x squared plus mx is being squared, right? And then what I'm doing is I'm saying that as xy approaches 0, 0 along mx, what I'm really saying we should do is take the limit as x goes to 0, right? So we want the limit as x approaches 0 of this stuff. Can I simplify this? Yeah, I can quite a bit. I mean, in the numerator, I want to point out that we have an x cubed times, it would be what? M cubed minus m, right? Is that okay? Because there's x squared and x, so the x cubed comes out. You guys with me? Now the denominator, what's the greatest common factor in the denominator? Well, I guess we have, isn't it true that I can take out x to the 4th? Maybe that's too fast. Okay, let's go slower. X to the 4th plus, see, I'm squaring a binomial, so it's square the first. I have to square the last also. Let me square the last. The last would be, boy, it's m squared squared, so it's going to be m to the 4th x to the 4th is at the last. And now what about that middle term? You get m squared x squared times x squared. So, and then you get 2 of those. So it's 2 m squared x to the 4th. How's that look? When I square a binomial, I get a trinomial. You guys with me on that? I'm just trying not to bog us down too long here. So here I go. Limit as x goes to 0, because I'm trying to move towards the origin along some line. Right now, if I plugged in 0, I would get 0 over 0. That's indeterminate. But what do you think I'm going to do here? No. I'm going to do it easier than that. Yeah, let's reduce, right? You could, I guess, L'Hopital's, but if I just factor things out and cancel, I guess if I factor out the x to the fourth, the only thing that'll be left out front is an x. And in the numerator, what would I have then? I would have, or the denominator, I would have a 1 plus 2m squared plus m to the fourth. Is that right? Yeah, you could factor that also. So you get, when you take, let's see. Yeah, m squared plus 1 squared. That's right. Okay. Now, what does this limit equal? Well, okay. It depends. If m equals 0, this limit is 0. Right? But if m equals anything else, like 2, well then you have some number in the top and some number in the bottom, but the x is going to 0. This limit is infinity. Does that make sense to you guys? Because as the denominator gets close to 0, the number gets huge. Okay? And so what this proves, okay, this proves that f of x is not continuous at 0, 0, even though it is defined. So this is a lot like the Calc 1 absolute value example. Absolute value of 0 is 0, but you don't have a derivative of an absolute value function at 0. The same thing here. The partial derivatives exist. You could do the same thing with fy. You could show that it's not. The partial derivatives exist, but they're not continuous at the origin. So, yeah, there's one more exercise to do with this involving second partials, but maybe we'll wait till after break for that because it is 11 o'clock, and I think you guys probably need it at this point. Here's a challenge for you guys. Here's a challenge for you guys, okay? We have this example, this function that I've been playing with, right? I was working all through here. I'm going to have you guys compute the second partial derivatives. So what I mean by that is fxx, fxy, fyx, and fyy. Do you understand what I mean? No. Okay. So let me help. Well, actually, let me help first of all. Let me cut the workload in half. Let's only compute fxx and fxy. And I'll show you why I'm going to do that in a moment. Okay? Although maybe you know. But what am I talking about? When I say fxx, what does that mean? It means, look what we have. Which formula do we care about? This guy, right? So when I say compute fxx, what are you going to do? Take the partial with respect to x. When I say compute fxy, you're going to take the partial with respect to y of the thing in pink. Are you with me? Actually, I wonder if we should make it a competition. All right, let's do it. So here we go. One group's going to do that. The other group is going to concentrate on fy. And you will compute fyx and fyy. And we'll see how good we are. So let's see. I guess, how about this half of the room? So everyone from Aaron and Kathy over here. You guys have the pink. You're going to compute fxx and fxy. And this half of the room, you six, are going to compute fyx and fyy. And I will pause, and then we'll come back together and talk about some answers. So let's work out fyx. And I guess maybe as a reminder to myself, I'll write down what fy was. So we know that fy, I'll write over here on the side, is equal to, are you guys using the formula x cubed minus xy squared? Or maybe I said y squared x last time?
Yeah.
Over x squared plus y squared squared. That's what fy equals, is that right?
Mm-hmm.
Okay, so now I want to compute fyx. Here I go. So I'm pretending that all the y's here are constants. So here I go. fyx equals Hody high. So it's x squared plus y squared squared times the derivative of the top, but I'm taking the derivative with respect to x, I'm treating the y's as constants, so it would be times 3x squared minus y squared, because y squared x is just becomes y squared, right? So far so good? Minus Heidi Ho. So Heidi Ho would be, well, I need the numerator, so it's x cubed minus xy squared times what? The derivative of the denominator. So we get bing, a 2. And then we get bing, x squared plus y squared to the first power, because I lowered the exponent 1. And then bong, the chain rule tells me I need 2x, right, plus 0. So there's my numerator, all over x squared plus y squared to the 4th power now, because I'm squaring the denominator. And I have a question to you people working on pink. Isn't it true that this is equal to what you guys got for fxy? Let's check that. Wait a minute.
X and Y are switched though. So instead of a 3x squared minus y.
Let's check that. Let's check that. Here's your fxy. Oh, I see what you're saying. 3y squared minus x squared. Ah, that's what you guys are saying? Well, I'm going to claim this is true. I'm going to claim they're equal. They don't look equal yet, but I'm going to claim that if we simplified that messy numerator, I'm going to claim they're equal. And in the book, they probably give me a nice little theorem that says when they're equal. The answer to that question, when are they equal, is almost always. What I mean is almost any function you can think of, fxy is going to be the same and equal to fyx. Let's see what they say about that. Is there a theorem? I think so. 13.4, let's look at it. 14.4 for us. Aha! Assume that f is defined on an open set, that fxy and fyx are continuous throughout D, then they're equal. Do they prove it? No. Look right above, guys. The proof is found in advanced texts. Okay, so be it. Thanks to Alexis Clairaut, who lived in the 1700s. Here we go. It turns out that most of the functions we encounter in this book have this property. Okay, so could there be an exception? Yeah, there could. But you're probably not going to have to worry about that too much. Okay, good to know. All right. What about fxx and fyy? Those are going to be different, but you can get them by swapping variables like you guys explained to me also. So let's see what we get for fyy. So same thing, I'm going to mess around with this and use the quotient rule. Oh, okay. Well, first of all, the x cubed goes away, right? Oh, but I need quotient rule, so here I go. Ho d high. So again, I'm going to start off with x squared plus y squared squared times the derivative of high is going to be 0 minus, now x I'm treating as a constant this time for fyy, so it's going to be minus 2xy there, minus high d ho, so the high would be x cubed minus xy squared, d ho, again that's bing bing bong, 2 times x squared plus y squared to the first power, but this time it would be times 2y all over x squared plus y squared to the fourth power. Right? Okay. So, question. Are these second partial derivatives defined everywhere? Well, almost. They're defined everywhere except what? When x and y is 0. So at the origin is our one worry. Ryan, you with me? Okay. So now my question is, can we define these at the origin? Could we talk about, for example, fyy of 0, 0? Well, not with that formula. So if I want to talk about this, what do I have to go back to? A limit definition, right? Limit as what? As h approaches 0. Of what? Let's fill it in. Let's fill in the denominator. Nice job, guys. Let's fill in over here. It's interesting. What I'm going to subtract is fy of 0, 0. Did we define fy of 0, 0? I think we did. Oh, I guess I didn't actually compute it. Up above, I computed fx of 0, 0. Right? Yeah, let me see if I did that. Yes. Here, guys. Remember we did fx of 0, 0 was 0, and I said similarly fy of 0, 0 is 0. Okay? So here I go. That's 0. What goes up here? Fy of 0, comma 0 plus h. Okay? So this is the limit as h approaches 0 of something minus 0 over h. What's the something? I need fy of 0, comma h. Now guys, there's the formula. If I plug in 0, comma h, I get 0 in the numerator. And don't I get h to the fourth in the denominator? Isn't that right? So I get 0 over h is 0. So see, it does exist. fyy. Okay. But what about fyx? Fyx of 0, 0. Let's see. That's using this guy, right? Ooh, that's ugly. Although maybe if I plug in 0, 0s, it won't be so bad. Oh no, I can't plug in 0, 0s here, right? So how do I do it? I say it's the limit as h approaches 0 of What do I put over here? Well, again, we're using fy. What's the difference? If I'm taking the partial with respect to x, it's going to be fy of 0 plus h, comma 0, right? And so the difference is, this is the limit as h approaches 0 of what? H in the denominator, I'm subtracting 0 because that's fy of 0, 0. But now here, we're plugging the h in for what in the formula? In for the x. So the denominator is still going to be h to the 4th, but what's the numerator going to become? Isn't it going to become h cubed minus 0? Do you see that? H cubed minus 0 when I plug in h comma 0. Now h cubed over h to the 4th is 1 over h, right? And then I'm dividing by h. So this is the limit as h approaches 0 of 1 over h squared. And so what would you say about that? I would say that does not exist. Or I might say it equals infinity. But the point is when h goes to 0, this blows up. Okay? So, what's the take-home message from here, Paul? I mean, we did a lot of work. First of all, are you guys able to compute the formulas in Brown? You guys able to compute that? If you are, then you could probably do most of the functions we're going to deal with, because those are some pretty nasty quotient rules. And again, those of you that did fxx, I guess I have it here. Okay, you can kind of check. It's almost the same thing. It's just switch the x's and y's. But for something that the formula doesn't work, you can still sometimes get results by using the actual definition of the derivative. So maybe that's the take-home message here. Okay, time for the chain rule. So here we go. And by the way, 225.